In the last unit, we found out that gradients are just derivatives of our tensor operations. We already knew that derivatives are useful for finding the minimum of a function, either analytically if we know the function of the derivative, or incrementally if we don't. The most exciting tensor operation for our purposes is the loss function, and of course that's the function that we want to minimize. Just to make sure we're on the same page, the loss function we're dealing with here is categorical crossentropy, which compares two probability distributions. In our case, it's the probability distribution of softmax with the actual probability distribution of the correct label that we created when we prepared our data. All these pieces should start to fall into place now. Mini-batch stochastic gradient descent has been around for a while, and it turns out that there are some difficulties in this. One of the biggest concerns people had was that you actually never know where the global minimum is. Take a look at this simple diagram. We have three minimums. Two are local minimums and one is the global minimum. Given the point where we happen to randomly fall on the function, if we continue downhill, we would imagine that we'd end up stuck in a local minimum and never realize that we didn't reach the global minimum. There are a couple of things to think about here. The first thing to realize is that the amount that we change x is determined by the magnitude of the derivative. The change in x will get smaller and smaller as we approach the minimum, since the gradient is also getting smaller and smaller. This means that training will take longer and longer and longer until it gets excruciatingly slow. To account for this, the adjustment was made to add momentum to the amount that we're going to change x. Gradient descent with momentum is typically faster than standard gradient descent. To see this in action, let's take a look at a more complex function. Remember, in our models, we'll have hundreds of thousands or even millions of parameters, so we can't visualize that, but we can look at a two-dimensional function, as shown here. Imagine that the third axis with color is the output of our function, the loss that we want to minimize. Here we have again two local and one global minima. I'm going to collapse the third axis into a 2D plane, maintaining the colors, and just visualize the depth as concentric rings. It's kind of like a topographical map. The more concentric the rings are, the smaller the function. In a map, the more concentric rings would show us the depth of the oceans and the heights of the mountains. Let's imagine we begin our gradient descent here. So far in the story, what happens is that we update our weights and then we end up here, and then here, and so on. So it takes a lot of steps as we slowly oscillate to the minimum. The steps become shorter and shorter as the gradient gets smaller and smaller. Remember the step parameter in our formula? That ensures that the adjustment we make is quite small, because if we use a large one, we may end up overshooting and end up far away from the minimum, like in this case. So we don't want to be jumping around too much, and the further away from the minimum we are, the more likely it is that we're going to overshoot and miss the minimum entirely. For now on, we'll call this eta, the learning rate. In this function, we only have two axes that we'll have to navigate to get to the minimum. We'll draw them like this. On axis 2, we want the adjustments to be small, because you can see that actually, if we didn't change anything on axis 2 at all, we'd still end up on the target. Another way to think about this is that if we took the average of all the gradients, we'd end up on zero change on axis 2. It's on axis 1 that we want to actually make the changes. In contrast to axis 2, the average of axis 1 continues to point towards the minimum. So any change on axis 2 is actually wasted computing time. Momentum tries to streamline the path to the minimum by using these averages. That means it doesn't just take the gradient of the current value W0, but it also uses information from previous gradients. Not only that, but the values are exponentially weighted averages that gives greater emphasis to recent values than distant values. In the end, this means that momentum uses information from previous mini batches instead of only the current one. There are two advantages to doing this. First, we smooth out the path to the minimum so that we increase our conversion speed. In addition to this, momentum also prevents us getting stuck in some local minimum. If we just use traditional gradient descent, it could be that we slowly approach some local minimum. But momentum means that we don't decrease speed as much as the gradient gets smaller, and that prevents us from getting stuck in a local minimum. Momentum is exactly what it sounds like. Instead of slowing down as we reach the minimum, because the gradient is decreasing, we're going to pick up a bit of speed, like a ball gaining momentum rolling down a hill. So nobody uses just mini-batch stochastic gradient descent. You're likely to see some kind of momentum. The kind that we're going to use is called RMS prop. RMS prop is an optimization method that tries to account for the wide range of magnitudes of gradients by dividing the gradients by a moving average of the root mean square of the gradients. Every example we'll go through in this video course will use RMS prop, and right now there's no reason to use an alternative. However, we will see some cases where we'll change the learning rate eta. Why is the magnitude of the gradient such an issue? This may sound like a completely new topic, but we've already encountered it. Recall when we prepared the MNIST dataset that we standardized the values from between 0 and 255 to between 0 and 1. The idea there was also to reduce the magnitude of the gradients, to limit the range of values our gradients could have. RMS prop is consistent with that. The reason we want to avoid large gradients is that it makes it difficult to choose a single global learning rate eta. If we can reduce the range of values in our gradients, using a single eta will become more appropriate. Okay, so that was a lot of information. I hope that by now you have an idea of what the optimizer and loss functions are doing, what gradients are, and what gradient-based optimization is. Gradient-based optimization is one of the key ingredients in the deep learning secret sauce. The other key ingredient is backpropagation. Let's head over to the next video and see what that is doing.